Welcome to LT Physics. We're going to show you an example of an object on an incline with an additional force acting on the object that's not parallel to the incline. And for this one, we're going to say there's no friction. We'll do another example later on where there will be some friction, and we'll try something else out. So for this one here, let's say we have an incline. Here's our block. I'll put it on wheels because there's no friction. And we'll just call that M. There's only one of them. And we're going to have a force pushing on the cart that's parallel to the ground, not the incline. We'll call that F, all right? And we're going to calculate, and the angle of the incline is theta. We're going to calculate the acceleration of the cart. And the first thing you got to do is guess which way you think it's going to go. Is this force big enough to accelerate the cart up the incline? Or if this force is too small, the cart will actually accelerate down the incline. So for now, we'll guess up. So this is the positive direction, okay? And I'm going to go ahead and draw an FBD. So here's our block, okay? There are three forces acting on it. We have F. We have the force of gravity, which is mg. And then we have the normal force, which is perpendicular to the incline, about like that. And just like always, we're going to split our forces into components that are either parallel to or perpendicular to the incline. Well, Fn is already perpendicular to the incline, so we don't got to do anything with that. But with F and with mg, neither of them are parallel to nor perpendicular to the incline, so we have to split each one into components. So I'll redraw the FBD over here. Fn is all good. mg, we're well accustomed to splitting that into components. The two components are mg cosine theta and mg sine theta. Now F, you got to be careful with. F has two components. It has a component that's parallel to the incline and a component that's perpendicular to or trying to kind of push the cart into the incline. If you look carefully, the cosine and sine is going to be different. The triangle we're going to draw, there's a component that's into the incline, and there's a component that's parallel to the incline. The angle we have here, that's your theta. So the component that's of F that's parallel to the incline is actually F cosine theta. And I'm going to draw that force bigger. So F cosine theta, because we're assuming the cart's accelerating up the incline, and then you have a smaller component that's F sine of theta pressing the cart into the incline. Now, assuming the cart's not crashing through the incline or jumping off the incline, this force has to equal the addition of these two, because the net force in this direction is 0 because there is no acceleration in that direction. So the only direction I have to look at is the direction that's parallel to the incline, and I'm going to call up positive. Again, I'm assuming it's going to accelerate up. So if I do net force equals ma, and here I'll put parallel to the incline and parallel to the incline. Okay, well, I've got two forces parallel to the incline, positive, negative. So I got F cosine theta minus mg sine theta equals ma. And if there's no numbers, the only other thing you can do is isolate a by getting m by itself. So a equals F cosine theta minus mg sine theta all over m. And there's nothing you can reduce there, so that is your answer. And then, of course, they would give you numbers. One thing to note, if you do the math, if this number is smaller than that one, then you've guessed wrong, and the cart will actually accelerate down the incline, which is fine. Your answer is still the correct magnitude. It's just now you know the cart's moving the opposite way than you suspected. So that's an example of an object on an incline without friction with a force additional to gravity and a normal force.